Hey guys, so this will be your first online lab. This one is going to be over the AM radio. So we'll talk about kind of in general, more in general terms, how AM radio functions. And this is sort of the culmination of everything that we've talked about up until this point. Basically, everything that we've studied is going to be included within this one lab. Okay. So how this will work going forward and today is that I'll do an introduction, and then afterwards you will see the procedure carried out in lab. So we'll first do a theory, talk about the theory of how AM radio works, and then we'll actually go through the procedure. So when we get to that portion where we're in lab, you can actually follow along in your manual and see us do the procedure step by step. And then if there is data, we'll post data online, and you'll be able to use that to then write your lab report and do your analysis. Okay, so for AM radio, let's just get a general idea of kind of how it works and what the whole system looks like. So what we have first is you or anybody else, right? And you're going to be singing into a microphone, which is then going to produce some small signal that we can then amplify. Now, what you could do with this signal is we can run it to a speaker, in which case we would be amplifying it, and you would hear it being louder. Okay, but if we want to transmit this small signal over much larger distances than, say, just the confines of whatever venue you happen to be in, right? Sound waves aren't going to cut it. Right, they attenuate or they dissipate much greater than say an electromagnetic wave would. You can see this even if you've ever been to a music festival, right? If you're far away from a stage, not only is the volume much lower, but also the sound quality is much poorer. Okay, so when we're trying to make sound waves travel over larger distances, we have to first convert them into electromagnetic waves, because electromagnetic waves attenuate much less in air, right? They can travel much further, and we have much less loss of power in the process. So it's a much more efficient process. So what we do is we do something called modulate. So our first step in this AM radio is we take whatever our signal is, right? Or we take whatever the small signal is, and we use it to modulate a carrier wave. Okay. And we'll talk about all of these steps in more detail. This is just your general idea, and then we'll go through and talk about each one in more detail. But we modulate a carrier wave using this small signal produced by you talking to a microphone or wherever your signal is coming from. And then we broadcast that signal, which can then travel much further on the order of miles versus on the order of meters, right? Whenever we were just talking about sound waves. All right, so we modulate the signal, we then transmit it using an antenna. All right, and then on the other end, some distance away, we have our radio that can now pick up this transmitted signal. So we first have to receive it. So we have another antenna on this end that we use to receive the signal. And in this lab, you'll see us actually making one of these one of these antennas, and the antenna is actually going to be an inductor. Right, so we receive the signal, and then before we pass this to eventually our speaker, right, for our radio, a few things need to happen to this transmitted signal. We need to filter it, right? So that because this is not the only transmitted signal. There will be many other signals being transmitted. So we want to filter out only this signal. And so we're not, whenever we do go to the speaker, we don't get a lot of noise, right? We only want to hear the specific signal that we want to hear. So we first need to filter it. Then we need to demodulate it. And we'll talk about what this modulate and demodulate mean in a little bit more detail here in a second. Basically, reconvert. So we converted this signal to an electromagnetic, and then we need to reconvert it into a signal that we can then send to the speaker. And then we need to amplify it so that we can actually hear it. Right, so these three things all happen before we actually reach the speaker, and then once we reach the speaker, you're then able to hear your music, right, or whatever it is that you're trying to send. All right, so these waves are traveling and then being picked up by this receiver. All right, so this is the general idea of how an AM radio works, right? We transmit a signal using electromagnetic radio waves, and then we receive it, and we then filter, demodulate it, and amplify it, and then we hear what we want to hear. All right, so let's talk about each one of these steps in a little bit more detail, starting with this first step of modulating it. So turning these sound waves into an electromagnetic wave that can then be transmitted. So we have two different types of modulation. Well, there are more than two, but two that we're really going to talk about today. And really only one that we'll talk about in any depth, right? So the ones that you're probably most familiar with are going to be the AM and the FM modulation. All right. So for each of these, right, we will start with the same signal. So we can transmit the signal that this guy is going off in either of these two, but the signal itself will stay the same. So you'll get some varying small signal coming from you speaking into the microphone or wherever else your signal is originating from. And in both cases, this will be the same. We want to transmit this same signal once using AM and then once using FM. Then we're going to use this signal, this small signal, to then modulate what we call the carrier wave, or the wave that's actually going to be transmitted between the two antennae. And so this carrier wave needs to be obviously an electromagnetic wave, and it needs to have a frequency high enough that it can actually travel that, or high or low enough that it can actually travel the distance that we're looking for. All right, so we have some EM frequency wave that we can then use this to modulate that and then transmit it. And so what we're going to do is, so the way that this signal wave modulates our carrier wave is different between the two. So we have AM modulation, which is amplitude modulation. So let's talk about that one first. That means we're actually modulating the amplitude of this carrier wave using this signal wave. So if we see what that looks like, right, we'll have an envelope. It's called the envelope, which is determined by our signal wave. And we use this envelope determined by the signal, or our modulating signal, to then modulate the, sorry, you couldn't really see that. There we go. Okay, so we use the amplitude, or we use this signal to modulate the amplitude of this carrier wave. So this is the envelope created by this modulation, and then inside of it we'll get this high frequency carrier wave, and the amplitude will change depending on, right, that envelope determined again by the signal. So our transmitted wave will look something like that, right? All right. Now for FM, instead of modulating the amplitude, it's going to modulate instead the frequency. So this transmitted wave now will have the same amplitude, right? But wherever our signal has a high intensity or a high voltage, we're going to have a high frequency. So if we draw in our signal, something like this, right, wherever these peaks are high, we'll have a high frequency. And then it's kind of hard to draw. And then we go high again, and then it starts to come down as this intensity comes down. So anywhere where we have a high peak, we have a high frequency. Anywhere where there's a low peak, we have a low frequency. All right, and the amplitude here is constant. Okay. So those are the two types of modulation. So we can then take this information and then transmit it and then receive it, and then we'll do these three things with filter, demodulate, and then amplify. Let's talk about some of the pros and cons between these two different kinds of modulation. So we have our AM over here, and we have our FM over here. So first, let's talk about kind of what is the frequency that we typically transmit at for these two different types, right? So AM, it has a pretty small transmitting range. So it's typically from 540 to 1600 kilohertz is the range in which we broadcast or transmit. And then for FM, we go from 88 to 108 megahertz. Right, so FM broadcasts over a much larger range than AM does. Okay, and that's because we'll see in a second that FM has a much larger bandwidth, meaning we need a lot more space between our radio stations than we do for AM. Okay, now these numbers should look familiar to you, especially these FM numbers, because these correspond to the radio stations that you see on the radio, right? So they're written in terms of the frequency that they're broadcast at. So one benefit of AM is that we can transmit over large distances. Because we're transmitting at a much lower frequency, the signal is attenuated much less, so it can travel much farther. Okay, so that means FM can travel not as far, right? But the thing with FM is we get a much higher sound quality. And this is due to a number of things. First is the fact that it has, again, that high bandwidth, meaning there's a much more space between stations, right? The bandwidth here is like on the order of like 200-ish kilohertz, and the bandwidth over here is on the order of like 20 kilohertz, which again, the bandwidth is just like the space that you need between each station. So you wouldn't want to have two AM stations that are closer than this number here, or else you wouldn't be able to resolve the station. So yeah, this higher bandwidth means we're able to separate the stations out more, and you get less interference between the stations. You also have the fact that noise doesn't impact an FM signal. Right, because what is noise? Noise is fluctuation in the amplitude, right? We don't care about amplitude for FM modulation. We only care about how is the frequency changing. So if one of these peaks gets a little bit higher than the other one, it's not going to really matter because the frequency isn't changing, right? Whereas in AM, if we get some noise, where if this peak here is a little bit higher, then we'll get a little blip in our envelope, which will then correspond to a blip in our signal that we'll get at the other end. Okay, so noise is much larger impact for AM, so you get generally much less, your quality is much less for an AM signal. All right, for AM, because it has a small bandwidth, you can have more stations within the same range, so we can get a larger number of stations. So that's one other benefit for AM, and then for FM. One actually drawback for FM is it's impacted more by physical barriers. So impacted by barriers, like walls, or you've probably seen this whenever you go underneath a bridge, right? Your radio station cuts out, right? And that's again due to the frequency that we are broadcasting in. For these higher frequencies, it gets attenuated attenuation means like we get less signal, or the signal is shielded, right? And this is due to multiple processes, either absorption or reflection, diffraction. So or refraction, any number of things can make this signal not penetrate a barrier, and this attenuation goes up depending if our frequency goes up. So for lower frequencies, it can pass through objects much easier than it can if we have a higher frequency. Okay, so these are some of the pros and cons. You can see why FM would generally be the better choice, just because we get a higher quality signal. But today we're going to talk about AM because building an FM radio, it turns out to be much more complicated than doing it for the AM case. Okay, so going forward, we'll be focusing more here, right, versus here. But just know that this is sort of how FM radios work. Okay. So yeah, now let's talk about the next part, which is, so we've talked about how we modulate and then transmit. So now let's talk about what is receiving our signal. So receiver. Okay, and I already told you in this case we're using an inductor as a receiver, which is just a coil of wire. And then in the case of our antenna or our inductor, we're also going to have a ferrite core. So we're going to have a core that we're going to wrap the wire around. Okay. Now, typically for radio antennas, you want the length of your antenna to be equal to about half of your wavelength, right? In this case, we can actually get away with having a much shorter antenna because of this ferrite rod. So the ferrite will confine the magnetic field, which will then, so it confines the magnetic field within this, which then kind of boosts its effective length, right? So it acts as if it's longer than it actually is. Okay, and now this receiver or this inductor is able to pick up the signal because we have, as we send in this oscillatory EM wave, right, it induces a current in the solenoid, right? The same way that putting a magnet in and out of a solenoid will induce an EMF and then a current, right? The same way as if you put it into a changing electromagnetic field, which is what light is, or what a radio signal is, you'll then induce a current within that solenoid. Okay, so this is how we're able to receive a signal and then convert it back into an electrical signal. So we take the electromagnetic light and then it's now converted back to an electrical signal that we can then do the rest of we can then filter, demodulate, and then amplify. Okay, so next step after we've received it, right, is to filter it. So let's move that out of the way and let's talk about filtering our signal. So again, if we have our antenna here, right, and we have multiple different signals coming into this antenna, and we only want one, right, and all of these signals are coming in at a different frequency, we only want one of them, what we have to do is basically build a filter here before it travels in. And this filter is going to be a bandpass filter. So this is something that we've talked about before, but just to give you, again, a really brief overview of what this looks like. So we have our alternating signal, we have our resistor, and then bandpass means that these capacitor and then our inductor, which again is also our antenna, are going to be in parallel. And then we have some ground over here, right? So this is our LRC bandpass filter. Okay, and so what it looks like is if we look at the gain for this bandpass versus the frequency of our incoming, right, you get a resonance frequency for a bandpass. So at some frequency, F naught, we're allowing the signal to actually flow, or we're allowing the current to actually flow within the signal. At all frequencies to the left and to the right of this resonance frequency, we filter them out. So if we are looking for a specific frequency, let's say that this signal incoming up here has a frequency F naught, right? We need to select our inductor and our capacitor such that this F naught is the same, or this resonance frequency is the same as the frequency of the incoming signal that we want. Okay, and the relationship, if you remember, to this resonance frequency for an LRC circuit and the inductance and the capacitance is just 1 over 2 pi square root of LC. So we can use this equation and we can use the fact that we know what the incoming frequency is to tune our circuit. So this is for tuning. So when we talk about tuning our circuit, this is what we mean, is selecting the L and C. And typically this inductor and this capacitor will be variable. So we can, as you're changing the station on your radio, you're actually changing the value of either this inductance or this capacitance. Or that's, at least that's how these radios used to work, right? Okay, so that's how we tune and filter out all of the things that we no longer want, or all of the signals that we don't want. So once we've selected the signal that we want by tuning our circuit, we then have to demodulate it. So let's talk about demodulation. Oh man. Demodulate. Yeah. Demodulation. Okay, So we have our incoming signal that we've selected by filtering, right? It looks like what we did before. So we have this envelope that's determined by our, again, by our modulating signal, or the signal that we're putting into the microphone. And then it's being carried by this high frequency carrier wave. And so this is our modulated signal. Now we need to find a way to convert this back into the signal that we had before. So basically all we want is this top envelope, right? And so to do that, what we first have to do is cut out this bottom section, right? We no longer want that bottom negative section. So to do that, we're going to use, in this case, there's a number of different ways to do that, but what we can use is our half-bridge rectifier, basically a diode, right? Because diode will only allow the current to pass in one direction, so we can filter out all of these negative currents. Okay, so here we're using a diode or some other means to filter out the bottom. So we're left with only this top envelope, and then still we still have this high carrier frequency or carrier wave being modulated by that envelope. Okay, now to get just this envelope, what we want to do is filter out the high frequency carrier wave. So how do we filter out a high frequency, leaving only this low frequency envelope? Is we use a low pass filter. So we use low pass RC filter. So again, something that we've seen before, right? A RC filter will allow high frequencies in, will allow a low pass will allow low frequencies to pass through the circuit, and it will filter out all the high frequencies. So what we're left over is, after we pass this signal that we've cut the bottom out, if we pass that through an RC filter, we're then left with only this signal, which is what we want. Okay? And then we can take this now demodulated signal and then send it to an op amp or a transistor or whatever we want to then use to amplify it. Okay, so you can look at your manual and see how these are able to amplify. Again, I don't want to go over that all again, but we basically send this small signal to one of these types of amplifiers, or any type of amplifier, so that amplified signal can then be heard on the speaker. And then at this point, we've now completed the entire process. So again, coming back to here, right? We talked about how do we modulate a signal. We then transmit it. We then receive it with our inductor, right? And then we filter it with a LRC circuit. We demodulate it using the process we just talked about, and then we amplify it using a transistor or an op amp, right? And then we're able to actually hear it on the other end. So this is what you would have done in lab, is you were really only going to worry about this second part, right? In lab, what I'm going to have set up, or what we would have had set up, is some signal that we're transmitting in the room. Okay, so we would do this whole modulating and then transmitting signal, and then you're going to build a radio that will then receive, filter, demodulate, and then amplify the signal so you could then hear it. Okay, so that's what you'll see next in the next section, or when we go to lab, is you'll see first a demonstration of this whole modulation and then demodulation technique, and then you'll actually see a completed radio circuit that will demonstrate for you. Okay, so this is how we'll do these labs going forward. Like I said, all needed data will be also posted on Canvas that you'll be able to use to then do your analysis. And then week to week, we'll be posting each of these videos at the time that your lab would have taken place. And so you can watch each of these videos and then be able to complete the lab report by the scheduled time. Okay, so we will see you in lab here in a second.
Hello, this is Jacob. I'm going to be running through the radio lab today. And I guess just as a preface, I'm going to try to cover everything that you would have done in lab, maybe kind of, skipping over parts that like where you would actually build the circuit and other components, maybe like this inductor, just because it's a bit unwieldy to try to make the circuits and film it, and probably kind of waste of time as well. Also, I guess, kind of bear with me. This is the first time I've done something like this, so it might be a little rough around the edges, a little haphazard at points, but hopefully I'll be able to convey all the pertinent information, and you'll at least get all the understanding that you would have had you been able to do the lab yourself. So I'll begin with a quick introduction of the lab. Evan's already given you the background kind of physics and things, but as far as the experiments in the lab and how it's going, first part is creating an inductor, which is going to act as our antenna for our AM radio receiver circuit. So the first part of the lab is constructing that, which you see right here. And then in the next part, we will be finding the inductance of this inductor, by creating a simple LC circuit, series LC circuit, and then finding the inductance over the entire inductor, and then kind of at this halfway point. It's not quite halfway, so this is slightly closer towards this side than that side. So there's 3 different values of the inductor that we're going to find. So this is the full inductance, and then this is called the center tap. And so we'll find the short end center tap and the long end center tap. After that, we're going to hook it up into a parallel LC circuit, and we're gonna tune it. So the idea behind it is there is a specific frequency that we are going to want to pick up. It's the AM radio carrier wave frequency, because that's what's carrying our modulated signal. And the way that we're going to pick that up, we're going to tune our components, our capacitor and our inductor, such that the carrier wave frequency corresponds to our resonant frequency. And so in this next part, the tuning part, we're just going to show how varying these components, changing their inductance and changing the capacitance, changes the resonant frequency. So it's pretty simple. We're going to be using the Fourier transform function to demonstrate that. After that, we're going to take a break from the inductor and create a modulated signal. So we're going to be using the signal generator to kind of create this pseudo carrier wave, and then modulating it and then demodulating it, so that we can see what a demodulated wave looks like. And then after that, once we have our antenna, our way of tuning our antenna, a way of receiving a modulated signal and demodulating that signal, we create a circuit that puts it all together and receives an AM radio signal, which, again, I wish you guys were able to do this one on your own. It's a pretty cool lab, but yeah, let's go through it. So first part is creating this solenoid, and it's fairly simple. We start off by, if we follow along in the lab manual, with a ferrite core. And that's just because it has a high permeability. We wrapped that ferrite core in paper, as you can see here, and that's just so that we can kind of easily slide it in and out of our coil. We then, once it was wrapped in the paper, we wrapped the copper coil around our ferrite, starting from this end right here, and going about 30 turns until we reach this point, and we create this center tap, which is just an extended piece of wire. So we, if we were wrapping it, we'd make a longer piece and then keep wrapping it again. And we're going to use this in the experiment to show how we're effectively changing the size of our inductor if we start, if we're measuring the, if we attach it into our circuit from one end to the center tap, we're effectively only using this much of the inductor. But, and it has some other purposes in the final radio circuit as well. So after the center tap was created, you keep wrapping until, you complete the, go to the end of the inch-long ferrite rod. And then you have your inductor. So I kind of skipped over this part again because, you guys want to sit here and watch me wrap a coil. Doesn't seem very fun. All right, I'm going to go over the LC series circuit to find that we're using to find the inductance of our inductor. All right, so this is the first circuit that we're going to be building for the lab, and it's to measure the inductance of our antenna. It's just a simple series LC circuit, and if you remember, it's also called a band stop filter, if you remember from that previous lab that we made these and measured the resonant frequency. And that's exactly what we're going to do again. The equation for resonant frequency is F equals 1 over 2 pi square root of the inductance times the capacitance. And since we are setting our capacitance, we'll be able to find our inductance at that resonant frequency. The lab manual suggests that we use this 100 nanofarad capacitor. The one that I'm using and that I measured is 100.2 nanofarads, so you'll need that number for your calculations. Okay, and just to briefly talk about the setup of the oscilloscope, I have channel 1, the yellow, be the output, be this voltage drop over the entire circuit, so over the capacitance and the capacitor and the inductor. And I went ahead and added channel 2, which is just the voltage drop over the inductor. So just from here to here, and then yellows from here to here. All right. So, so you'll see that. And we are trying to find the resonance frequency. So we'll start at a low frequency and then work our way up until we find our resonance value. So just to give a reminder of what we're actually looking for, we'll be measuring this voltage drop over both components, and because this is both these are in series, there's the same current flowing through both of the components, but the voltage drop is different. And as we increase our frequency, the voltage drop is going to change over both these. But there's going to be a value where it's the same, and that corresponds to our resonant frequency. And we're actually going to get a minimum value, a minimum output, when we measure this channel 1. And that's because that the voltage over a capacitor will be, or should be, 180 degrees out of phase with the voltage over our inductor. So when they're at the same value, they should, kind of destructively interfere with themselves, and we should get this, ideally just a zero voltage kind of line of short in our circuit, but it's going to be, you're still going to see some waveform. But that's it. That's all we're looking for. We're looking for when this yellow channel is at a minimum, and that'll be our resonant frequency. Okay, so I've built the series LC circuit. We can see that we are measuring over the full length of the capacitor, so this should be our maximum inductance. And I have the signal generator set to 5 volts peak to peak at 1,000 hertz, and I'm going to slowly start increasing the hertz or the frequency. We can see here that this channel 1 is the voltage drop over both the capacitor and the inductance. So we're going to be looking at this to see when it's minimized. And the channel 2 is just the voltage over the inductor. So that should start to increase as we increase our frequency. So let me go ahead and start increasing our frequency and adjusting the time scale. So we see that our channel 1 is decreasing and our channel 2 is, our channel 1 is decreasing, and our channel 2 is increasing. Oops, and we've kind of reached lower bounds. So I'm going to increase the scaling of our channel 1 just so we can really see when that minimum occurs. So it's right around there. Let me do this. Okay. So let's say it's right about here. So the resonant frequency for the full inductor is 44.3 kilohertz is what I'm measuring. All right, so 44.3 kilohertz. Now I'm going to change the lead so that we're measuring over the center tap to the longer end, so decreasing the inductance of our capacitor since there's fewer coils. So we should see that our resonant frequency should go up, and it looks like it's going to, since we see that our amplitude has already increased for our channel 1. So again, I'm finding the resonant frequency for the center tap long part of our inductor. So let me increase the frequency again. Okay, so it looks to be right about here, and I am measuring right at 60 kilohertz. So 60 kilohertz. So that's for the center tap long. And that makes sense. Like I said, the inductance is smaller, which is inversely proportional to the resonant frequency. So smaller inductance, larger frequency. Okay, now let's do the last one. So we're going to do the center tap short now. So changing this lead so it's right here. And now let's see. A little wobbly. Okay. Okay, so I'd say it's right around here. And let's say that's minimum value is right at 98.8 kilohertz. And that's for our center tap short. Okay. So those are all the measurements. You can calculate the inductance from those. Just to run through them once more. For the full inductor, I got 44.3. For the center tap long, I got 60. And for the center tap short, I got 98.8. Okay. All right. So now that we have measured the inductance of our antenna, we're going to show the process of tuning to a specific resonant frequency. We've switched out our 100 nanofarad capacitor for a veritable 60 to 160 picofarad capacitor, so much smaller, 3 orders of magnitude smaller. And the way that this circuit is set up, it's now a parallel LC circuit, so it's a band pass filter. So it's really only going to want to select frequencies centered around the resonant frequency. And by slightly changing the value of our capacitance and even our the value of our inductance, we can change what that resonant frequency is. And that's exactly what we're going to do. We're going to be, showing how changing these values affects the specific frequency that our circuit is tuned to. I don't think it matters really, but the 100 or 1 mega ohm resistor that I'm using is actually 988, but I don't think you're going to be using it for any calculations. And one other important thing to note is that we're not sending in just a pure signal, we're sending in a noise. So it's going to be, a bunch of signals, and this will kind of make more sense when I have both the output and the Fourier function kind of set up on the oscilloscope. But essentially, we're sending in a bunch of signals, and it should select out the signal that is centered around our resonant frequency. So we should see a peak in our Fourier function. And again, I'll show you once I have it set up. So let's go to that. All right, so I went ahead and built the circuit. And we can see here is our Vout. Channel 2 corresponds to our Vout from figure 6. And this is the math function, the Fourier transform of this signal. And we can see it's a little messy, but there is a definite peak right here, which corresponds to our resonant frequency of our parallel LC circuit. And just to comment on what I have, the components for our circuit, the capacitor is a variable capacitor. And right now I have it set to its minimum value. So it's right around 60 picofarads. And as you can see, I'm measuring the total. I have the lead set up for the full width of our inductor. So we're getting the maximum possible inductance for our inductor. And like I said previously, this noise signal can be thought of as a linear combination of a whole bunch of random sinusoidal wave function, and it's just at different amplitudes, and it's all together, so we get something that's looks random and noisy. But there is a very particular frequency, the resonant frequency, that it's going to be amplified, and this peak in our Fourier space is corresponding to multimeter. Is corresponding to that resonant frequency value. So with values of our capacitor and inductor as they are right now, we can see. I'm going to stop it for a second. That's a pretty good one. So we can kind of see that our frequency of our amplitude is right around 1.08 megahertz, which is good because our AM signal that we're going to be receiving, the carrier wave, is going to be in that megahertz range. So that's kind of why we moved down to this small capacitor. All right, so for the rest of the section, we're going to be looking on how changing the values of our components changes the peak of our resonant frequency in our Fourier space. So let's do that. Let me get it going. So like I said, the capacitor is set to its minimum value, and if I adjust it, we can see that it gets a little muddled, but we can see that it's still roughly around right here. You see that it drops, and then if I keep going, and then finally I get back to its minimum value again. So I very quickly kind of ran through the full range of that capacitor's possible values. So as we see, as well as we increase the value of our capacitor, our resonant frequency lowered. So I'll do it once more. And I'd say that's about as low as I can get it. And just to kind of see what that corresponds to, it's about 900 kilohertz, so definitely smaller. All right, so let's put it back up to its minimum value. Sure. Right around there. Okay, so now let's see what happens when we change our inductor. So, like I said, we're going over the full range of our inductor from the further most leads. I'm going to change one of the leads so that we're measuring from the long side of our center tap. So let me, whoa, sorry. So now we've decreased the inductance of our capacitor since we made, since we're going from the, we're only going over half the full range of our inductor, half the physical length of our inductor. And we see that our peak is kind of shifted up to like around 1.49 megahertz. So much larger resonant frequency, which again, hopefully makes sense because we are decreasing our inductance, and that's inversely proportional to our resonant frequency. Okay, so now I'm going to switch the leads so that we are measuring the inductance over the center tap to the short end of the inductor, and we can kind of see that it's kind of past the range of our window. So the peak is kind of around here, but it's very spread out, and really it's kind of past our range. I don't think we're really going to pick up anything. I mean, if we go all the way to the end, we're seeing something around 2.49. I mean, that's not a very defined peak anyways, but we can see that it definitely still moves to the right, which again is consistent. So let me put it back to the way it originally was, measuring the full range of our inductor, and we can see that we have now again kind of gone back to this 1.8 megahertz frequency. And now let's change the inductance again by removing the ferrite rod inside the inductor. So I can't really show both things on screen. Well, maybe I can. Can I? No, it's not going to work. Okay. All right, so now the ferrite rod is completely inside the coil, and now, whoops, it is completely out. And now, so inside, out. So if I go slowly, we can see that as the rod is removed from the inside of the coil, the inductance goes down because its relative permeability decreases. So once more, fully inside, and then now it's fully removed. Okay. So I think that's good. All right, let's go ahead and get started on section 3. So in this part, we will be creating sort of a pseudo carrier wave using our function generator, and then modulating that wave, and then demodulating that wave, all in the same circuit, to kind of give you an idea of what an AM radio wave looks like although since we're using the signal generator, the AM wave is still going to be a very simple sine wave, but it still hopefully gets the point across. All right, so I went ahead and built the circuit from figure 8, and what I have shown right here on the oscilloscope is that channel 1, the yellow, is that V1 output from the figure, and it's just the raw output from our signal generator. So right now I have it set to 50 millivolts peak to peak. Yeah, 50. I think it's a little easier to see at 50. I think the lab manual says 30, but it's fine. So you can see here 50 millivolts peak to peak at 100,000 hertz, which is right. Oh no, which is right here. And then our V out is our amplified signal, which kind of is sort of half cut off because it's kind of reaching the bounds of our 9-volt DC window. But that won't really matter, especially when we get to the part of actually demodulating. But we can see that it is amplified. It's around 3 volts, 3.2 volts peak to peak. All right, so let us kind of zoom out to give you an idea that this, or just to show that this really is not a modulated signal. Now that I've zoomed out to this kind of much larger time scale, and we have such a high frequency, it just, all the amplitudes look close enough to each other that it's just one giant, rectangle, one blob. So there's no modulation. But let's use our function generator to modulate it. And in doing so, I'm going to set the modulated signal to 1,000 hertz, and the peak to peak, of that new modulated signal, I'm going to create using this AM depth. So right now it's at 0%, and we can see that, well, it kind of looks the same. There's no real modulation happening. But as you'll see, as I start to increase the focus, as I start to increase the AM depth, or as it's also referred to as the modulation index, we will start to see some modulation. And it's referred to a percentage because, as you'll see, as I'll show, the modulated signal is going to be centered on the peak value, the max value of our carrier wave. So at 0%, there's no voltage change. It's just kind of staying at that that maxed mean value. Oh my gosh, come on, can I get there? Let's get in. Okay. Max mean value. So as I increase the percentage, so now I'm at 20%, we can see it's still kind of centered, what would be centered, the max value, and now it's beginning to modulate. So if we set it all the way to 50%, we see that it's going down, 50% of what is our half of our peak-to-peak voltage. And if I were to set it up to 100%, well, now, if this was our old peak-to-peak, it's going now all the way down to what would be our mean value, so 0 volts. But for our purposes, 50% is good. And we can see down here that our demodulated signal, what will be our demodulated signal, the signal that we want is this guy right here. So if we zoom back in, though, it's our true wave that we have is this really fast carrier wave. So we need to find a way of getting this signal, because this is our modulated signal. All right, so in the next part, I will do just that. All right, so I went ahead and added the components from figure 9 so that we can fully demodulate our carrier wave. And you can see from the figure that we added a couple of capacitors, a resistor, and a diode. The capacitor and the resistors form another low-pass filter so that we can remove the high frequencies of the carrier wave. And the diode was just to select out the piece of the envelope that we were interested in. So we can see, put it all together, that we have a demodulated signal. And if you remember, when I set the modulation frequency of on the signal generator, I set it to 1,000 hertz, and that's exactly the frequency that we are reading right here. It's 1,000 hertz, and I can change that if I wanted to. So if I change my frequency to 2,000, it still is working. It's also interesting if we zoom in. We can start to see that our demodulated signal is still actually this carrier wave. It's the same frequency as our carrier wave. Just really, if we look at our scale, it's 5 microseconds for one box. So, our wave is roughly 2, so that corresponds to a frequency of 100,000 hertz, and so it's still kind of hidden in there. But zoomed out, we see that it just forms the wave that we wanted to modulate. So there's this guy with a much larger amplitude at 230 millivolts. Okay, so now that we can put both these things together, we'll move back to our inductor or antenna that we created, and we'll add it into a circuit so that we can tune to a specific frequency, the frequency of the AM signal that we will be using to output a song, and we will then, demodulate that signal and play that sound through the speaker. So I'll come back after we've made that circuit.
Okay guys, so here we are. We've got the radio set up, but before we show you that, I wanted to show you how the signal is being modulated. So what I have here, I don't know if you can see, but I have my frequency for my carrier wave set to 1.6 megahertz, which is within that range that we're looking for an AM signal. And then I have my amplitude of my carrier wave set to 20. So what we'll do now is we'll go ahead and use this modulate function that's included in our function generator. And there's an option down here. It might be hard for you to see, but if I click that, I can change it from an internal source. And if I click it again, I can change it to an external source. So this means that I can plug my phone or my laptop or whatever I want into the back of this machine, and then the carrier signal that we have set up at the 1.6 megahertz will be modulated by the signal coming from my phone or whatever device. Right. So right now we have this modulating our signal. We have our phone plugged in, playing a song that you'll hear in a second, hopefully. And I also have the oscilloscope hooked up to this thing. So if we look at the oscilloscope now, you'll be able to see that carrier wave being modulated. So you can't actually see the individual waves of the carrier wave because the frequency is so high. Let's see, if we change our horizontal axis, you might be actually able to see it. There you go. But it's easier to see that envelope or that modulation if we make it so small that you're only able to see that envelope of it. All right, so what we're going to do now is turn on our power supply. So here's the radio circuit here, right? We're going to turn on our power supply, which is over here, which is going to supply power to the circuit. So go ahead and click that on. And what you'll hear here, once we get it all plugged in, is a lot of noise, right? Because it's not yet tuned.
Should have just kept it in there.
Yeah, so... Alright, so we hear a lot of noise, right, because it's not yet tuned. So what we need to do is start to tune the circuit. So, yeah, so here's our variable capacitor. You can change the capacitance of this value just by putting in a screwdriver and turning it. So that's what we're going to do now. So you'll see him turning that screwdriver. And eventually, we should be able to hear our song. All right, there we go. So here you can see that these are not connected, right? This is my antenna here, which is hooked up to my function generator, and then there's the antenna. So they're not directly connected, but this is outputting a signal that is being picked up by that antenna. All right, so hopefully that demonstrates everything well enough that you can write about it. We'll go ahead and turn this power off so you can't hear that anymore. But yeah, so, right, we're taking that dismodulated signal, right, that's coming from this function generator, and then this circuit here is doing the three things that we talked about, which was it's first filtering it, and then it's going to demodulate it, and then it's going to amplify it, and then it's going to output from this speaker. All right, so that's going to be the end of this lab. Go ahead, your lab will be due so like a week and a half or 2 weeks from today, which is Tuesday. So just look on Blackboard if you're confused about the due dates. But this one will be a 1 week lab versus 2 because you weren't actually here to do it. And I'll make an announcement, so this will hopefully be clear. All right, that's going to do it.